Good afternoon, everybody, and welcome to day 4 of INSPYRE 2022, the International School on Modern Physics and Research organized by the Frascati National Laboratory of INFN, Italian National Institute for Nuclear Physics, and addressed to high school students attending their last 2 years. Today, the first lecture is devoted to astrophysics and in particular to the research field of gamma ray burst and is held by Cristiano Guidorzi. Cristiano Guidorzi is a professor at the Department of Physics and Earth Sciences of the University of Ferrara, Italy. He works in the field of high-energy astrophysics, time domain astronomy, and transient sky. I remind you that you can write your questions in the chat, and at the end we will answer to a few of them. Cristiano, the floor is yours.
Okay, thank you very much. Hello, everyone. So as you heard, I'm going to talk about gamma ray bursts. And you will understand very soon why I chose this title. The end is just the beginning. So just to start describing what a gamma ray burst is, as I wrote here, if we could see with our eyes the gamma ray sky, so you would see essentially a picture like this. Well, this plane is just the galactic plane. And then all of a sudden, just a source which just shows up, and it is so bright that it outshines all the gamma ray sky. And see here in the plot here, you see the gamma ray flux is a function of time. So just within a time interval of a few seconds, you will be just flashed out. So you clearly see that there is nothing like that in the visible sky. So the gamma ray sky is pretty weird. And gamma ray bursts are very, very powerful and unpredictable sources. This is an example of a few light curves. What a light curve is, well, this is just flux in the y-axis versus time in the x-axis. So you see that the variety is huge. For example, if you look at this one, you see that the duration is less than 1 second. So this is called a short burst. So pretty simple, as I would say. And then you have just longer burst with just one main pulse and then something following, and then much more complicated cases in which you see that this flaring activity just going on up to minutes, if not several minutes. This is a 300 seconds, so 5 minutes long, in which apparently there's no rule. Sometimes you've got some flux, and then most of the fireworks come later, or the other way around. So essentially, there is no periodicity in the signal. So apparently, there's no pattern easily that can be easily identified. There are by now we know that there are at least 2 families. Here you see duration distribution. So what is that? This is just the number of bursts as a function of their duration in units of second. This is a logarithmic scale, and so you see that there are 2 families essentially. The blue one, which is the short one. By short means well, there is an overlap, but let's say on average less than 1 or a few seconds, while the red one is just the long burst. Nowadays, we know that they correspond to 2 different kinds of progenitor. In particular, the short ones are due to and this is something that I will talk about more in detail later on, this is due to the merging of a binary system of compact objects, and we will see in particular binary 2 neutron stars, or 1 neutron star and a black hole, which at some point they merge together, and so the merging is just is supposed to be signaled by the emission of a short gamma ray burst, while the second family is due to is so-called a collapser. So it's due to the collapse of the core of some special kind of massive stars that I will be describing. So just to let you appreciate what kind of energy is involved. So just to make a comparison, let's consider our sun. The power, the luminosity of our sun, so energy per unit time, is about 4 times 10 to 26 watts. If you work out the total energy emitted, radiated by the sun during its whole lifetime, which is about 10 billion years, just multiply the 2 and you get something of the order of 10 to 44 joule. Well, the energy released within a few seconds, just in the gamma rays, which is not the whole budget, but just in the gamma rays, within a few seconds, you get an energy released which is comparable, if not larger, than the energy radiated by the sun through 10 billion years. So quite mind-boggling, I would say, and sometimes can be even comparable with the rest energy of the entire mass of the sun. So if you use the famous formula by Einstein, mc squared, where you take m, the mass of the total sun. So in principle, the highest amount of energy you can get out of the sun, sometimes the energy released within a gamma ray burst can be comparable to that. So really, really impressive. One of the important features that we understood about gamma ray burst is that the emission is not so-called isotropic. So it means that these gamma rays are released within a jet, and we know by now that the opening angle of the jet is just a few degrees. So essentially, you do see gamma ray burst whenever the line of sight is co-aligned, lies within this jet of a few degrees. In that case, you see a bright gamma ray flash. If you don't, just for geometric reasons, so for just the line of sight doesn't happen to lie within this cone, well, you might either you don't see any gamma ray burst at all, so we are not even aware that the gamma ray burst went off in that case, or you might see a very weak, very dim gamma ray burst. So as I told you, this is just a plot of the distribution of the opening angles as we measure them. It's pretty challenging from an observational point of view to measure these angles, but for the burst for which we succeeded, it is possible to make this histogram in which you see two different colors. The red one, the red histogram, is about the long gamma ray burst, so the one connected with the collapse of the core of a massive star, while the blue one is just the short burst. You see that there are fewer short bursts because it's more challenging, because they are weaker, essentially. So anyway, you see that for both classes, you see that, as I was saying, that the typical opening angle is just a few degrees. Let's say if you want to take a mean value, let's take 5 degrees, or anyway 5 or 10 degrees. So if you work out the probability that the line of sight just lies within this cone, let's take for simplicity 10 degrees, you work out the probability is just 1 minus cos theta, where theta is just this angle. 1 minus cos theta because there are two jets in antipolar directions, as shown here in this figure. So you see that essentially the probability, the chance probability of just having the line of sight within this cone is just about 1%. So it means that for every GRB that you observe, there are at least 100 that you are not observing just because of the jet axis is not pointing towards us. GRB are very, very powerful and also very important to study also the evolution of star formation throughout the universe. So here you see a very typical plot in which you see the different phases from the Big Bang here all the way up to nowadays as a function of redshift. And you know that the universe age is about 13.8 billion years. So the furthest GRB that we observe to date is called 090423. That it means it was discovered in 2009 on April the 23rd. And it was the furthest, as I said, essentially it went off when the universe was just 600 million years old. So in this way, by studying GRBs, in particular the galaxies where they are found to go off, we also have an independent probe, an independent tool to probe how stars formed at the very beginning when the very first stars were born. So they are very useful also as a means to study the universe as it evolved throughout the different ages. So there are a lot of things that we still don't know. This is just a collection that I'm going to review right now. So, for example, you might be surprised that we still don't know exactly how these gamma rays are produced, what kind of radiative processes are responsible for the emission of gamma rays. And in particular, we know that these two jets that develop In both classes, both short and long gamma ray bursts, they move at relativistic speed, so that there's the speed of the material which is ejected along these two jets is very close to the speed of light, very, very close. And we still have to figure out exactly how this works. And also, the nature of the progenitor, what is the star which is responsible? What kind of star? I told you in the case of long gamma ray burst, it's just the collapse of the core of a massive star. But we still have to figure out why just a tiny fraction of all the massive stars just end up with this relativistic jet.
Cristiano?
See?
Sorry to interrupt you. We
Yes.
have a question.
Yes.
How frequent are gamma ray bursts?
Oh, yes. On average, we see just 2 or 3 per day in a completely unpredictable way. So this is the average observed rate, just 2 or 3 per day, let's say.
Okay, thank you.
Okay. And so also, one of the key questions that people are trying to understand right now in the latest years is to understand how many elements, as we know them, also elements which are present in the solar system, elements which belong to our own bodies, how much of them, which of them are created in this kind of events. And I'll spend a few words later on. And so to some extent, the question is how much of the elements we are made of are just were created, were forged in this kind of explosions. And then one of the other question is, what kind of object is left over after the end of this explosion? Is that a black hole? Is that a neutron star? We still don't know, and I'll tell you more later on. So just to let you appreciate how all this began, how we managed to discover all this and the existence of these gamma ray burst sources. And I can tell you that the story just began some kind of, let's say, 50 years ago, when during the Cold War between Soviet Union, US, and other countries which had nuclear weapons, they decided they made a ban treaties according to which these countries were not allowed to carry out nuclear tests, too many of them. So the US, to make sure that people that the countries just adhered and didn't do these tests, they built up these satellites equipped with gamma ray detectors. So these gamma ray detectors, which were called Vela satellite, after the Spanish Vela, which means just to monitor, to ensure that everything is going on correctly. So just to monitor that nobody was carrying out a nuclear test on ground, because one of the products of nuclear test is just the production of gamma rays. But then in the end, it happened that they discovered that some gamma ray bursts were not definitely coming from ground. It took some years to understand this, because it's not easy to localize, to understand the arrival direction of a gamma ray burst, particularly at that time. But they used many different satellites. Essentially, the reason is that because you cannot focus gamma rays in the same way as you do with visible light. Gamma rays are so penetrating that they are transparent. So you need other techniques to understand the incoming direction. So they used many different satellites, and just based on the mutual delay of the detection of the same wave by different spacecraft, they could realize it essentially with an accuracy of a few degrees, which is pretty rough, but enough to exclude that the gamma rays were coming from the Earth. And so when scientists were pretty confident that these flashes of gamma rays were not coming from ground, well, essentially they discovered the astrophysical problem of gamma ray burst. And in that moment, the question was what kind of astrophysical sources? Completely unexpected. A very important progress was was obtained kind of 30 years ago when the CGRO, so the Compton Gamma Ray Observatory, which flew from the early 90s of the last century up to 2000, when it started measuring thousands of gamma ray bursts. Well, it couldn't localize very accurately. The typical accuracy was just a few degrees, which is not enough to pinpoint, to identify the source. Because if you take if you look at the sky in a field of view of a few degrees, there is so many objects that you cannot essentially hope to identify the counterpart, if any counterpart exists. But one of the results of the satellite was they made up this map. As I said, it is a color-coded map where the color just reflects the fluence. The fluence is just how energetic the burst is. So ergs per square centimeter means energy essentially deposited in gamma rays per unit area in the detector. And so essentially, this is in galactic coordinates. What does this mean? It means that the galactic plane, so the plane of the Milky Way, the galaxy we belong to, is just this plane. So you see no clustering around the galactic plane. So essentially, what we call there's an isotropic distribution. So the same concentration, the same number of bursts for any direction in the sky. And essentially, the possible explanation for this was just two different alternatives. Either the bursts they are so close to us, for example, on a solar system scale, that they do not have anything to do with the galaxy, or completely opposite. The second alternative was just they are so far away, much further than the typical distances within the galaxy. Of course, in principle, both of them could be correct. But if you consider that the gamma ray bursts in the gamma ray sky are so bright, if they are so far away in the universe, it means that they are very energetic. The definitive evidence, the so-called smoking gun evidence, came only in 1997, thanks to the Dutch-Italian BeppoSat satellite, which in the end managed to discover the so-called afterglow. What is that? Well, BeppoSat was equipped with a combination of X-ray and gamma ray detectors. Clearly, the gamma ray detectors were needed to alert people whenever a gamma ray burst was detected. But at the same time, the combination with an X-ray detector, the X-ray detectors, in the X-rays, it's much easier to localize with a better accuracy. And so you saw that in 1997, they managed to observe the X-ray counterpart. At the time, people didn't know whether there was a prompt X-ray counterpart. They just assumed. They said, look, in the case there is an X-ray prompt counterpart, we could manage to localize much more accurately, down to a few arc minutes. So one arc minute is 1/60 of 1 degree. And so then they had a look, they repointed within a matter of a few hours the most sensitive X-ray telescope they carried on board, that was aboard BeppoSat, and then they saw this very bright source just a few hours after the gamma ray burst. And I remind you, the gamma ray burst just lasts a few seconds, and then that's it. But then they discovered this longer-lived X-ray source, and then they managed to observe it a few days later. This was taken on February 28th, and then they got back to the source, and they reobserved it on March the 3rd, the same year, so just 3 days later, and they found the very same source. These are X-ray images. They found the same source which had faded significantly. So there was no doubt anymore that that was the source associated with the gamma ray burst. And then in the end, it was possible, a few months later, it was possible also to identify the host galaxy in the visible light. And by identifying the host galaxy, they measured the redshift. And so they could establish in the end that the distance were cosmological distances, so gigaparsec. And so once you measure the distance, you know the energy, the released energy, and so you start doing real physics. So what is the afterglow that essentially Beppe Sachs discovered? Well, while the gamma rays itself, so the event that lasts just a few seconds, is something which is still unknown. We have just a few ideas, but we are still pretty unsure how gamma rays, as I was telling you, they are made. We know much better about what the afterglow is. Well, the afterglow is observed from X-rays all the way down in frequency to optical and radio bands. It is way longer lived. We can observe them for days, weeks, if not months, in some cases years after the burst. It's a fading source. And what is the explanation for this? Well, imagine you have this ultra-relativistic shock. Well, this shock propagates not in vacuum, but within a medium, interstellar medium, which is the environment surrounding the progenitor star. And so this medium is shocked by this jet. And the result of this shock is that the interstellar medium just starts emitting radiation throughout the entire electromagnetic spectrum, so X-ray, optical, and radio bands. And by studying the properties of this longer-lived emission, we understand quite a lot about the energy released, the density of the medium, the kind of environment, and so on and so forth. After Sachs, the satellite SWIFT, which was named after Nick Gettles, who was the PI of this experiment, which is still operational, was still being discovered in gamma bursts. It's already 18 years almost. It carries on board 3 instruments: the Bartlett telescope, which can localize promptly gamma ray burst within a few seconds, and it automatically repoint its X-ray and UV optical telescope within just little longer than 1 minute, 100 seconds, and can localize gamma ray burst down to in a very, very accurate way. As in almost all cases, I would say down to a few arc seconds. And when you localize an event within a few arc second accuracy, well, you essentially enable the search for the host galaxy and also the distance measure. By now, essentially, SWIFT discovered 1,500 GeoBays, one third of which, so for 500, let's say, it was possible to measure also the distance. So a great improvement with respect to the Beppe Sachs time. So let's focus a little bit on the two families. In particular, let's focus about what we've learned about long gamma ray bursts. So it's about the collapse of the core of a massive star. How we managed to understand this? Well, essentially, because we saw in the cases in which the GRB was close enough to us, we managed to detect a supernova associated. And we know that the kind of supernova that is associated, this is the very first case in which we observed a gamma ray burst associated with a supernova. It is called GRB 980425 because it went off in 1998 on April the 25th. And by the way, this is still the nearest long GRBs that ever detected. It was detected by Beppe Sachs at the time. It is just 40 megaparsec away from us, which is essentially, I would say, 130 million light years away. It might surprise you. I said the nearest, yes, because we are talking about cosmological events that lie at cosmological distances. So this distance in this scale, it means relatively nearby. We understood this because we found a few days later these light curves in the optical bands, which are the signature of a supernova, and this is the name of the supernova, and this is the spectrum as a function of time. So the flux is a function of wavelength taken at different epochs from the GLB. Taking the supernova spectrum, we understood essentially that a supernova was associated with the gamma ray burst, and by measuring these lines, we understand what kind of elements were created and how fast they are moving, they are expanding from the Doppler effect, and we found that very large expansion velocity, greater than 10,000 kilometers per second. And the second one, we didn't observe any hydrogen, which means that the progenitor star, whose core collapsed and gave the gamma ray burst, had no outermost hydrogen layer. So it was a massive star, but in the context of massive stars, it was a relatively compact one.
Cristiano?
Yes,
Sorry
please.
to interrupt you. They are asking if you can repeat what is afterglow.
Yes, an afterglow is essentially what is a longer-lived emission that we observed from the X-rays all the way down to optical and radio bands, which is the leftover of the initial explosion. You observe the gamma ray burst, which lasts just a few seconds, and that's it. In the gamma rays, you don't see anything else. But in the longer wavelength range, we see this source, which is a fading source. So you need to be quick if you want to discover it, because the longer you wait, and then the fainter the source. And this is due to the interstellar medium, which is shocked by this ultra-relativistic jet. So this longer-lived emission, which we call afterglow, well, the name just comes after because it's what comes after the main glow, which is the gamma ray burst, and is due to the interstellar medium, which is shocked. It's shocked by this ultra-relativistic jet. And so the result of the shock is that this medium starts emitting radiation, which is the afterglow. I hope it's clearer now.
Yes, thank you, Cristiano.
Okay, so what is the object which is left over? What is, we don't know yet, but we think that either a black hole which is powered by an accretion disk. So all the matter which is just surrounding the black hole keeps being accreted, and this accretion contributes to power the ultra-relativistic jet. But this is not the only possibility. Another possibility, and see in this picture, you see the jet is just drilling through all the progenitor star, which in the meanwhile is expanding because of the collapse and then of the explosion of the star. But there could also be a neutron star with a very powerful magnetic field, which is called magneta. So we still don't know exactly which of the two. Could be that both scenarios are possible. So let's move now to consider what short gamma ray bursts are. This is a completely different family. And as I wrote here, and as I told you at the beginning, this is something to do with the coalescence, so the merging of a binary system made of two compact objects. What these compact objects are? Well, there are two possibilities. Either two neutron stars which are orbiting one another, or a mixed system made of a neutron star and a stellar black hole. Stellar black hole means a black hole with a few solar masses. And how we managed to understand this? Well, there is an important date I will comment later on, which is 2017, in which when something very, very important just occurred. Before 2017, essentially, we understood already that short gamma ray bursts must have been something different. In this figure here, if you look at the red points, in the y-axis, you see the luminosity of the supernova that we found in association with the gamma ray burst. So all the red dots, all the red circles are long gamma ray bursts, the one I've just talked about. And you see that more or less all the long gamma ray bursts were found to be associated with a supernovae that are more or less equally luminous. When the short gamma ray bursts instead were close enough to enable a search for a possible supernova, we never observed any supernova. And the result is just this upside down triangle, blue triangles. What are these triangles? Well, these triangles means they are so-called upper limits. Upper limit means there is nothing up to this value, or there could be something fainter. So if there is anything, it must be fainter than this, and so on. So you clearly see that if there is, the possibilities are just two. Either there is no such supernova associated with a short gamma ray burst, or if there is a supernova, it must be significantly fainter, way less luminous than the supernovae that we see in association. So this already told us that, okay, short gamma ray bursts must be something different. Was this the only evidence? No. For example, when we compared the properties of the host galaxies, we saw that while for long gamma ray bursts, the host galaxies were all galaxies with a high star formation. Why this? Because massive stars, the one associated with long gamma ray bursts, as you probably know, massive stars live very short in astronomical standards. Very short means a few million years, which is so. In order to have massive stars, when you see massive stars, it means that you are looking at a region where star formation is still going on. While if you do the same exercise and you study the host galaxies where short bursts were found, we saw that in some case the host galaxy showed no star formation. So, and also the distance between short gamma ray bursts and their host galaxies were much larger than the typical distance between long gamma ray bursts and their host galaxies. All these evidence points to suggested that short gamma ray bursts must have something to do with older stars, with older systems than what long gamma ray bursts did. And so the possible scenarios for the progenitor systems of short gamma ray bursts is just shown in this beautiful figure, in which you see that either if you have a double neutron star system, so two neutron stars orbiting each other, or a neutron star and a black hole, so depending on some parameters, in particular on their masses, at some point they merge together, and the result could be just a stable neutron star, massive star, or an unstable neutron star, which then at some point collapses to a black hole, either passing through an accretion disk phase or just directly, so this transition should be accompanied by the emission of a short gamma ray burst. You might wonder, how do these binary systems form? Well, you end up with a binary system of neutron stars, for example. If you, at the very beginning, when the system is born, you need to have two massive stars. And then the two massive stars, each of which just, within a matter of a few million years, just collapses and then just ends its life as a supernova. And so the leftover object of a supernova is a competent object like a neutron star. So, and at this point, and this is just the blue line, it's just the timeline, which just takes a few million years, because massive stars live very short. So in the end, when you end up with such a binary system of a couple of neutron stars, if they survive and the system is not disrupted, because they could get a kick velocity and just disrupt the system. So if they manage to survive this, then they orbit each other, but they lose energy because of the emission of gravitational waves. But this process takes billion years. It's a very long process. So even from moving from here up to the point when they finally merge, it takes billion years. So inevitably, when the two neutron stars are close enough to each other to finally merge, then we see the short gamma ray burst, and we also see the gravitational waves. Well, we thought we should see, but until 2017 we couldn't know, because the gravitational wave detectors were not sensitive enough up to 2017. So our story, so the emission of a short gamma ray burst essentially marks the end of the lifetime of this binary system.
Cristiano,
Yes,
sorry.
please.
we have a question. What kind of radiation is emitted by supernovas in addition to gamma ray bursts?
Well, this is an interesting question. Essentially, if we stick to electromagnetic radiation, at the very beginning, at the time at which the core collapses, you don't see anything yet. Because light, the big amount of light that is created as the result of the nuclear radioactive decay, because in the core collapse, there is a lot of radioactive material which is produced. And so a lot of gamma rays that are produced inside the star, but the outermost layers are so thick that radiation cannot escape. You have to wait for a few days after the core collapses. And then you start seeing the light curve in the visible UV just increasing and then peaking, typically, let's say, a few days or 2 weeks, more depending on the kind of supernova, and then it declines within months. This is in the optical visible light, something that you can use your own telescope if you want. But if you consider also non-electromagnetic messengers, neutrinos are the very first thing that you would immediately see in the very first seconds of the core collapse, because neutrino interact just weakly, so they can escape much more easily than what photons do. So if you include also neutrinos, that would be the very first. And by the way, neutrinos are those which take most of the energy released. What we see in the electromagnetic waves is just a tiny fraction. So let's say 1% of all the energy released and carried away by neutrinos in a supernova explosion.
Thank you, Cristiano.
You're welcome. So as I said, the story had a big twist and a very, very milestone in August 2017, on the 17th of that month, because on that very day, there is something which we can consider as the birth of multi-messenger astrophysics. What happened is, in this famous figure, in which you see that the gravitational interferometers, LIGO in the US, the two LIGOs in the US and Virgo in Italy, they saw the signal. What is this? This is the intensity of the gravitational waves, and in the y-axis you see frequency of the signal, and here time, the increasing signal marking the coalescence, so the merging of a binary energy star system. This event was called GW 170817, so 2017, August 17th. GW stands for gravitational wave. And in space, the satellites, in particular two satellites, Fermi and Integral, just less than 2 seconds afterwards, they detected a short gamma ray burst. So these purple light curve is just the counts measured by the gamma ray detectors, and so they indeed saw a short gamma ray burst just less than a few seconds after the very merging, compatible with the same direction in the sky. And so this alerted all the astronomers in the world to search for an optical counterpart. And so the search went on, and they finally managed to find the optical counterpart. What is this? Well, this is a time lapse of the optical counterpart, just as a function of time, days after the gamma ray burst. So you see that they found a fading source, and this is the host galaxy. The host galaxy is a galaxy at 40 megaparsec away. So as I said, 130 million light years away from us. And if you wonder, how does this short burst compare with the typical population of short bursts? Well, this is the luminosity of the short bursts in the gamma rays as a function of redshift. The blue points are just the long gamma ray burst. The orange one are short bursts, and this big star is just the event that we measured simultaneously with the gravitational waves. So you see that this is luminosity in a logarithmic scale, and this is the value 10 to 47 ergs, which is still, well, a lot compared to the sun. It's just, as I said, 10,000 billion times more luminous than the sun. But in a context, in a GLB context, this is so-called underluminous. We could, this dashed green line marks the sensitivity of our gamma ray instrumentation. So it means that for all the events lying below this line, even if they are, we cannot see them because they are too faint. And so the fact that we could detect this event, it was just because it was very, very close to us. And if you wonder how far could it be provided that we could detect, well, we could have detected it only at a distance which is twice as far away as it would be. So if you put the very same event beyond 80 megaparsec, we wouldn't have detected it with the current instrumentation. So in a sense, we were very lucky. So it was close enough to allow us to detect the gamma ray counterparts. This is a simulation of what we think happened. So you see the binary neutron star whose frequency just increases as they get closer and closer, and now you start seeing the emission of gravitational wave up to the point that finally there is the merging and then the release of the ultra-relativistic jet. So I told you that there was also an optical counterpart, which is called the kilonova. What is this? Well, there are two components. Let's focus on the first one that was detected in the radio and X-rays days and several days after. So the so-called afterglow. What is this due to? Well, this is due to the relativistic jet. And depending on the line of sight, we expect a different evolution of flux with time. In particular, if you monitor how flux evolves with time in a log-log plot, well, when the line of sight lies just within the jet, we are expected to see something like this, where a straight line in a log-log plot is a power law decay. Well, if, for example, the line of sight just lies slightly off the jet, we are supposed to see an initial increase and then a fading. And if you are more off axis, if the line of sight is well off axis, then you are supposed to see something way fainter with a peak time which is delayed. So you might wonder, what did we see? And the result is, well, if we call the theta ops the observing angle, so the angle between the jet axis and the line of sight, essentially these are the data. This is the evolution of the radio afterglow from here all the way up to the X-ray afterglow. So you see, these are days, 100 days. So we managed to kept observing the evolution of the source for years. And so you see clearly that in the end, the kind of evolution allowed us to infer that the viewing angle was between 20 and 30 degrees. So that also explains why we saw this much faint, much less luminous short gamma ray burst with respect to the population of long gamma ray bursts that we usually see. Okay. But there is also another component, the optical component, which I showed you, if you remember the time lapse that I showed. What is this? This is so-called kilonova. And this is visible in the UV, visible infrared. This is due to the radioactive decay of all the material which is created in the aftermath of this. And what is this? Well, we have to distinguish between two components. The so-called red kilonova, which is the one here, which lies close to the plane of the orbital plane of the binary systems, and the polar direction, which is blue. What is the difference between? Well, you have to imagine that in this disruption of neutron stars, you've got a lot of neutrons that are freed. And so free neutrons can contribute to the creation of a lot of radioactive nuclei. Depending on whether you create nuclei, depending on the abundance of neutrons, you might create elements whose mass number A is greater than 140, let's say, or lighter than 140. So depending on whether you've got a lot of neutrons, you end up with creating a lot of heavy elements, and so you end up with the red component, and this depends on the direction. So depending on the line of sight, you are expected to see something bluer or something redder. So why is this? What happens during these events? Well, there are the so-called, depends on the processes through which these radioactive nuclei are created. In particular, during the events of the binary neutron-star merger, we believe that the so-called R process takes place, is dominating. What is the R process? R stands for rapid neutron capture. What happens is that in this environment, you've got a lot of neutrons. And so you've got nuclei, you've got these radioactive nuclei, which can gain a lot of neutrons very fast in a rapid way, more rapid than the time it takes for the radioactive nuclei to beta decay. So the beta decay is when the neutron just turns into a proton, and then it releases also an electron. Given that you've got so many neutrons, in this kind of environment, these radioactive nuclei acquire a lot of neutrons before beta decay. And so in this way, you build up in a very quick way, as a matter of seconds, a lot of radioactive heavy nuclei. While the slow process is something which typically happens in environments which are not so full of neutrons. So in this case, in the case of a binary neutron star system, you've got a lot of neutrons. So this is the process we think takes place. Why is this important? Because if you look at the table of the elements with which I'm sure you are familiar, you might wonder which elements are supposed to be forged during a merging of a neutron star. Well, the answer, you see, all these relatively heavy elements, you see this purple color tells you how many of them are supposed to be due to be produced. And so you see that a lot of heavy elements, in particular lanthanides and actinides, but also iron, you see that there is strong reason to believe that quite a sizable, if not most of the iron you are familiar with, were just billion years ago, were made in this kind of events. So this is pretty interesting. So this is also important. So this is the so-called kilonova evolution. So this is the flux in the optical that we measure as a function of time, days after the explosion. So depending also on the amount of heavy elements, you are supposed to see a bluer or redder components. In the case of the August 17, we saw both. Why? Because the line of sight was kind of in between the polar and the equatorial direction. So that's why we managed to see. And this is essentially a sketch which just summarizes what we think happened. So essentially, this is the line of sight here, I say around 20 degrees. The angle, the jet angle is just a few degrees, it's kind of 3 degrees. And we also could measure, we could also estimate the amount of heavy material that was produced. And this is tell you a black hole question mark. We think that the leftover object in the end must have been a black hole, but we are not very sure about that. In particular, we are not sure about how long it took to form. And one of the other very interesting aspects of this event is that this merging of binary neutron star is another independent tool to estimate the Hubble constant. Why? Because from the gravitational wave analysis, you can estimate the distance in a completely independent way of the electromagnetic signal. But when you manage to measure, to identify the host galaxy, when from the optical spectrum, you can measure the recessional velocity, so the redshift. And so by measuring independently the velocity with which the host galaxy is receding from us and distance, you have an independent way to measure the Hubble constant. Why is this so important? Because nowadays, different ways of measuring the Hubble constant are giving slightly but significantly different values. So we still do not understand why this. So having the possibility to measure this through a completely independent way, this is very important to understand. So there's a slide just to give you a hint of all the possible implications of studying these events. You can do cosmology, for example, by constraining the Hubble constant, but you also understand nuclear physics. Why this? Because based on the analysis of the gravitational waves and the electromagnetic waves, you can understand you can constrain the so-called equation of state. So how mass in the neutron star that then got disrupted managed to live. We still don't know, because we cannot reproduce in the lab densities that are typically found in neutron stars. So from understanding these properties, we can infer the properties of matter at nuclear densities, and also the astrophysics, and also test of general relativity. For example, this event was the very first case in which we could measure the propagation velocity of gravitational waves. And one of the predictions of general relativity is gravitational wave propagate at the speed of light. And so this was tested to a very high level of accuracy. You could also make this kind of test. You could wonder how many such events are supposed to take place in our own galaxy, the Milky Way. Well, from the gravitational wave data, we measure that in the Milky Way, these kind of mergers happen on average, one every, let's say, a fraction of 100,000 years. So imagine this, and then you can wonder, okay, if you look at the galactic radio binary pulsars, so binary systems made of pulsars are just pulsating neutron stars, which are still way before they finally merge. By counting them, we know how old they are. We estimate a rate of 20 per mega million years, which is equivalent to something very comparable to this. So this is a so-called sanity checks. An independent way to estimate this gives you more or less the same value. You can go further, and you can wonder, okay, we measured it from the very event of August 17, how much material, heavy material, by heavy, let's say, with a mass number greater than 90, how much material was forged. And we measured just a few percent of a solar mass. Now, assuming that every binary neutron star merger produces the same amount of heavy elements, and given that we can measure the abundance of these heavy elements in the solar systems and all the way out throughout the galaxy, you might calculate what's the rate of binary star mergers required to explain the observed abundance. And if you carry out this calculation, you end up with, again, something very comparable to this. So this is telling us, okay, these events are, if not the most contributor, a sizable contributor to the creation of these heavy elements. So there is a sizable fraction that the gold you have among your stuff, it was just forged a billion years ago in an event like this. You might also wonder, are gamma ray bursts dangerous for our own life? So do they have to do with mass extinctions? You know that there have been at least 5 documented mass extinctions well, the question is how dangerous they can be. Yes, if the gamma ray bursts go off within a few kiloparsecs distance, so a few thousand light years from us, the effect can be very, very nasty on us, because they can ionize the atmospheric gas. In particular, they can destroy the ozone layer, and by destroying it within a few seconds, there is a powerful UV flash that can reach ground, and so can harm all the living species. And also you've got the ionization of nitrogen with the production of a lot of nitrogen oxides in particular, that they can react and they can make acid rains. And if you wonder about the probability, well, this plot tells you as a function of distance from the galactic center, and we are at 8 gigaparsecs, so the red line is where we lie. This is the red curve is the probability that at least one short gamma ray burst, so the binary neutron star merger, went off and it's close enough to damage us, and the solid black line is the probability, the same probability for a long gamma ray burst. So you see that the probability that at least one lethal gamma ray burst struck the Earth during the last, for example, 500 million years is about 50%. Is there a mass extinction which could be compatible in principle, as much as we know? Yes, there could be the so-called Ordovician mass extinctions that happened 450 million and 50 million years ago that could in principle be compatible with the effect of this. So what's gonna happen next? Well, next year, if the pandemics or other problem are not going to delay it, there will be SWAM. SWAM is a Chinese-French satellite, which will be the SWIFT successor, and is an optimized version, essentially, of SWIFT. And again, it will couple gamma ray instrumentation on board with ground stations in the optical domain that will be constantly monitor the field of view of the satellite to catch the optical afterglow. What about the gravitational wave interferometers? Well, this plot again shows you the observation periods, the periods during which these gravitational interferometers observed are divided in so-called observing run. 01, 02, 03 have already been done. Here you see the timeline. So towards the end of this year, for at least 1 year, the LIGO Virgo will start the so-called OFO run. And here you see distances. These are the distances within which a binary neutron star system will be detected by the corresponding detectors. So we expect to see, we calculated the probability of seeing another event like the one we saw in August 17. There is a very good possibility of observing such an event like this, at least another one like that. So in the next, so stay tuned from December this year, because we are expected to have very good, interesting news from the gravitational and electromagnetic wave. If you are interested in what's going to happen much further, much beyond, so in the 30s, there will be two major gravitational wave interferometers, the Cosmic Explorer in the US and the Einstein telescope in Europe. Their sensitivity will increase by a factor of 10. We are supposed to see thousands binary neutron star merger every year. So very, very exciting prospects for the future. And that is all I wanted to say. So please, if you have questions, I'm ready to take them. Thank you.
Thank you, Cristiano, for this very remarkable and very wonderful talk about gamma ray burst. A question or just a comment. So gravitational waves go along with gamma ray bursts, and how important is to have an international network between all these observatories, sharing data and so on. It seems to be very, very important, the teamwork in this field, right?
Absolutely, absolutely. In fact, the possibility, something that I didn't have time to say, but the accuracy with which the gravitational wave interferometers can localize, can pinpoint the direction of a gravitational wave source is several degrees, which means looking for a transient source in the electromagnetic field within a field of several degrees is like looking for a needle in a haystack. So having a broadband and a network capable of reacting in a very effective way to search for, in particular with the gamma ray detectors. So the possibility of having space detectors capable of localizing the gamma ray burst within a few minutes is key to help the optical astronomers to find the optical counterpart. Something that I didn't tell you, but the optical counterpart that was found for the event of August 17 was found 10 hours after the burst. Even if the short gamma ray burst was discovered promptly, because the gamma ray burst was relatively weak, so the accuracy was a few degrees, and the accuracy of the gravitational wave was several degrees squared. So in that field of view, there is thousands of galaxies to search for. So that's why it took 10 hours. So this is absolutely important, also because you are looking for a fading source. So if you are not quick enough, then the source becomes too faint beyond the instrumental sensitivity.
Arianna is asking, could you please explain again how magnetars work?
Oh, essentially, what is thought to be a mechanism powering gamma ray burst is that the leftover compact object is a kind of neutron star with a very strong magnetic field. This magnetic field, when the magnetic field axis is misaligned with respect to the rotational axis, there is an effect in classical electrodynamics which works as a braking mechanism. So the neutron star, which is spinning at the beginning very fast with a period of a few milliseconds, so it's spinning 1,000 times per second, it spins down because of this magnetic braking. And by spinning down, all the rotational kinetic energy is turned into electromagnetic radiation through some kind of mechanisms. So this is supposed to be powering, for example, the gamma ray burst emission. So it's just kinetic energy of the very fast spinning star, which is just converted, which is gradually being converted into electromagnetic radiation. Okay. So, and the result of this is the spinning down of this object. So they are called magnetar, just to mean magnetic stars, because their magnetic field is, we say, of the order of 10 to 11 Tesla. So it is orders of magnitude larger than what we can make in the lab. If you take that, if you compare with the most intense magnetic field we can create in the lab, this is just ridiculous. These objects have a magnetic field which cannot be reproduced in the lab.
Davide is asking, is general relativity capable of explaining gamma ray burst, or is a new theory needed?
Well, to explain the production mechanism of gamma ray burst, yes, in principle, you need general relativity to carry out a fully self-consistent simulation. But essentially, general relativity is important, first, to predict gravitational waves, and second, to predict exactly, to model what is supposed to take place to the object, which then gets formed. But the mechanism which is responsible for the gamma ray burst itself, so for the gamma rays, is something which takes place at much larger distance. I didn't say that, but if you consider that the compact object is of the order of 10 kilometers size, typically, few tens kilometers size, where the gamma ray burst is supposed to, we still don't know, but it's something which is some kind of energy which is dissipated, and this dissipation of energy turns into the production of these gamma rays. But this is supposed to take place, let's say, 10 to 8 kilometers. So way away, much further away from the compact source. At that point, general relativity is not so crucial. What is really needed is to understand this outflow. So is this material which is moving at relativistic speed, what is the mechanism responsible of converting a fraction of this energy into gamma rays? We have some ideas, of course, which are, of course, I cannot go into details, but we are still unsure exactly of the details of this. So the nature of this dissipation process is still to be clarified. So in this sense, to understand how gamma ray bursts are made, general relativity is not really necessary.
Okay, thank you, Cristiano. Thank you again for this very wonderful talk. Thank you to our students. Let's meet at 4:30 for the second talk. Please wait on this playlist for the next webinar to begin.